First of all, thank you very much, Barbara, for inviting me to this very interesting workshop. And I'm very happy to present my talk after Francesca, who actually is looking at the same phenomenon as I am going to do now, but from a little bit different angle. Okay, so what I am going to discuss is what are actually factors which influence or, let's say, control the maximum magnitude of subduction earthquakes. And I will look at this from side of modeler, and actually a modeler of long-term deformation processes, but now coming also to earthquake timescales. Okay, so first of all, this is what already was mentioned. So the previous very famous analysis and concept of what was the key factor that controls magnitude of the earthquake was this paper by Raff and Kanamori. And actually, if you look here, so this is just citation from their paper. So they assume that mechanical coupling was a key factor, and this is not to mix with seismic coupling. So this is really mechanical coupling, and this is what they define like strengths of coupling between upper and downgoing plates as a product of the area and stress on contact zone. So this is really mechanical coupling. Okay, so as was already indicated by Francesca, it was very good fit at that time. So here I just indicated earthquakes with higher than 8.5 magnitude, and this is the line of 8.5 in this diagram of rate and age they suggested. So fit was very good, but erroneously, just after this paper, almost all big earthquakes they just violated this kind of this concept, and we can see this here, as also Francesca has mentioned. So this is a new diagram of so earthquakes versus these parameters, and I again highlighted here earthquakes which have magnitude more than 8.5, and the line. So all these points must go here above the line, and you see the most of these points are below the line. Okay, so this doesn't work, and of course this is not only in Here was indicated in Here 2011. Also in many other studies it was indicated that this doesn't work. The question is why actually it doesn't work, because it looks like a very natural and physical idea. And this will be one of the questions we will address here. Okay, few more observations also indicated before. So this is also the work where Francesca, I think, was involved. And what we see here, so this is sediment thickness in the trenches. And you see all earthquakes with magnitude more than 8.4, which are indicated here. And all of them are happening in the trenches where sediments are thicker than half a kilometer. Another observation also was indicated before, but this is, I'm stressing it more. So this is dipping angle of subduction zone. You see, again, all earthquakes with a magnitude more than 8.4 are happening at the subduction zones with quite shallow quite gently dipping subduction zone. And also here says this is regime of the upper plate. So you see here compressional with red and neutral with green. This is probably better could be seen in this diagram, where I put again all earthquakes with magnitude more than 8.4. In this diagram, deep angle and sedimentary thickness, and color is indicating the stress of strain in the upper plate. And we see again, so most of the earthquakes have neutral, so just almost not deforming upper plate above the interface, and only few of them have compressional and no extensional type of deformation. Okay, so now the key questions which I am going to address here. So first of all, we'll begin from looking on the strengths in subduction interface from long-term perspective. So what is the long-term strength of subduction interface? Why the largest earthquakes occur at low-angle subduction interfaces filled with sediments, with neutral or rarely compressional upper plate. So this will be the second question, and why the idea of rough and Kanamori doesn't work. Okay, so now this is the technique we are using for our modeling. So this is, we are solving a full system of conservation equations for mass and momentum and energy in full form. And what is important that we are dealing with all major deformation mechanisms in our modeling. So elasticity, viscous, or ductile deformation with complicated viscosity, and strain rates actually depending on stresses and on temperature in nonlinear form. And also we are using this non-associative plastic strain formulation, usually with more Coulomb friction, sometimes with Drucker-Prager formulations. Okay, so this is typical kind of model which I will discuss now. I will discuss now. So here, sorry, I didn't put. So this is the entire upper mantle. So 400 kilometers here, the scale, and 1-to-1. So basically, what we have here. So we have realistic upper plate, a realistic lower plate, asthenospheric material here, and what we are doing, we are pulling from below. So this is more, let's say, physically reasonable way of making subduction zones, because we take into account the rest of the slab, which is somewhere here, and pulling this part of the slab. What is important here, so we have a special rheology in what we call subduction channel. So this is just a very narrow zone between the two plates, where we have special rheology. This rheology also is viscoelastoplastic, but friction is lower. Or this is one of the parameters of the model, so it could be much lower. And also we have viscosity, which is ductile rheology, which is temperature and stress dependent, but it is very low. We just take the lowest experimental data for quartz, wet quartz here, or for serpentinite in deeper part for this kind of subduction channel. Okay, now this is what I am going to show you, what is happening with a slab if you pull from below and you put just 0.1 friction coefficient here. It's quite low from point of view of experimental data. So this is 40 million years lithosphere is coming in with a full realistic rheology taken, parameter taken with experimental data, temperatures and so on. And we pull from below. And this is just 2.5 million years, 3 million years. You see, the slab is broken. And this is with friction coefficient of 0.1. If we decrease here, so we go to 0 overriding rate, or put inside a colder slab, then this coefficient, friction coefficient of surviving for subduction zone is going to only 0.15. So no subduction zone can survive if friction coefficient, average friction coefficient here at the interface is higher than 0.1.15. Okay, now this is, we have done this in more details also for special cases. This is this Andes, Central Andes, and this is Southern Andes. And we modeled evolution of the system during 30 million years. And we got a very good fit of evolution and structures for Central Andes with friction coefficient of 0.05. And for Southern Andes, even much lower, 0.015. And this is, in South Andes, we think that this is because this very low coefficient, because of a lot of wet and soft sediments in the trench here. And this coefficient is probably one of the highest for subduction zones in Central Andes, because there is no sediments in this trench. So mostly what is coming in subduction channel is just sheared material from the upper plate. And this was also suggested by other people. So by Lam and Davis in 2003, they looked at recent balance of the forces in the system and came to basically the same results. Okay, this was not only we who suggested weak subduction zones. So actually, this is absolutely fundamental question for our planet. What are the conditions for plate tectonic? And usually, you just hear that this is convection, which is driving the plates, and this is very important, and that is condition for plate tectonics. And this is just only one very important condition. Another very important condition is weakness of plate boundaries. They must be very weak in order to for plates to move, and especially weak must be subduction zones. And we also looked at this. So many people suggested that. We also looked at this in more details, in more quantitative way. But first, let's also look from other side. So from modeling, we have constraints that subduction zones must be very, very weak. But do we have other arguments for that from completely different side? And the answer is yes. So now I show you the work by Gao and Wang. It was published in Science in 2014, and they looked at they tried to estimate friction based on heat flow observations in several subduction zones. And this is, those are magnitudes of the largest earthquakes at these subduction zones they looked at. And they put their results. So this is friction coefficient, apparent friction coefficient. This is maximum magnitude of the earthquake at this particular zone. And what you see, and they claim that there is negative correlation. So you have the largest magnitude of earthquakes are happening where you have the lowest friction coefficient. I would say, looking at the error bars of their data, I would say it would be more consistent to say that there is no correlation at all. Anyway, we can put here our estimations, absolutely from completely different side of looking on that. So this is our maximum friction for subduction zones. And here are our estimates for northern Chile, for southern Chile, and here is our estimate from global model. So what you see that two completely different approaches show you that subduction zones must be very, very weak. Okay, so this we'll have in mind for the next part of the story. And first, but first we just address the question why friction is so low, because we know from experiments it's much higher in dry rocks, and of course it was already suggested by many people that this is effect of high pressure fluid. So actually what we are dealing with is not real friction coefficient, but apparent or effective friction coefficient, and you can get it very low if fluid is, pressure of fluid is becoming very close to normal stress. And this is what how I explain this to my students. This is, everybody is driving the car now in our time. And this is, and this is what you see here is aquaplaning. So aquaplaning is effect. So you get a high fluid pressure here below the wheel of your car, and you then get a very unstable and very low frictional behavior of your car. And basically, subducting slabs are aquaplaning into the mantle. Okay, this is now, we are going to short term. So now we have to modify our model. So we start with large scale, long-term model of this kind of model, and then start to modify rheology to go to a smaller time scale. And this is what we have to introduce now to get stick-slip behavior. This is classical rate and state aging, rate and state friction law, which was demonstrated before in a couple of talks before me by Sylvain. So this is the classical way of look on this dynamic type of friction. And we introduce this in our subduction channel. We go to much smaller time scales. We are introducing adaptive time scale, time step gradually increasing from 40 seconds at earthquake. So we are not looking at dynamic rupture. It's just a couple of time step earthquake is couple of time step event in our models. But we are focused at the appearance of earthquakes by themselves and the rest of seismic cycle. And what you see here is what we get here. So this is seismic cycles. So this is time here. This is typically what we get as spikes, two-dimensional earthquakes. And you see here, this is what we get in late interseismic. So you see here we have, this is strain rate here. We have here creeping in the deeper part, a little bit of creeping in the uppermost part. This is locking here. And this is what we get in earthquake. You look completely different time scale for strain rate. Earthquake is usually going deeper than the locking zone. And usually it's coming to the surface when magnitude of earthquake is very large. So this is how we calibrate our rate and state parameters. Instead of using experimental data, we just calibrate them to get the realistic stress drop and period for the Chile 1960 earthquake. And this is those parameters we are using in the rest of the models. Now, we can look at subduction zones of different geometries. And also what we are doing, we are changing static friction coefficient in subduction channel. And these two parameters we vary in our modeling. Okay, so we have to compare with real earthquakes, we have to scale our two-dimensional model to 3D. And we are using scaling by Strasser 2010. And actually, this is hidden assumption in that is that we have a lateral coherency of our rupture to at least 3 rupture widths laterally. Okay, so now this is what the magnitude here, and this is dipping angle. And you see here the entire range of friction coefficients. So all this, each point are different friction coefficient and different angles of subduction zones. And you see the range of a maximum. So for each geometry and friction coefficient, we run 100 cycles and take the maximum magnitude. And this is now presented here. And what you see immediately, so this is friction, this is a dipping angle, and this is friction. So change of friction in this range is significant, but not the largest effect. The largest effect is dipping angle of the subduction zone. You see, you can look at again on this. So this is now this is one particular subduction geometry with different, so you see angles of subductions here, and different friction coefficients. Again, you see that subduction geometry is the major effect. Here you are looking, so completely different scale here, so from 9.1 to 1.96. This is effect of velocities. We change velocity by 3 times. Subduction velocity effect is very small. And you see here now all 3 effects together. So this is subduction velocity on magnitude, this is friction on magnitude, and this is angle of subduction zone. And so basically we can say that situation is quite simple. The angle of subduction zone is the most important. And we can say even a situation is even simpler. So now, at this plot, I put all my models just relative to one parameter, which is rupture width. So in all these models, what is important is rupture width. And so all these parameters, so all the angle of the slab, friction coefficients, velocity, they all play because they change rupture width. And you see here, this is what exactly suggested in 74. So all new things are forgotten old ones. So this idea was better than the next idea by Raff and Kanamori. And I think it was a great idea. And here you just see very obviously how actually angle of seismogenic zone affects width of rupture width. Obviously, slightly dipping has a wider seismogenic zone. This is how friction coefficient affects width of seismogenic zone. So by moving deeper, brittle ductile transition, it's going deeper if your friction coefficient is becoming lower. So that's why you increase your width of subduction zones. And also velocity changes a little bit by changing temperature in subduction interface. Lower velocity, higher temperature of subduction interface. Okay, now we can test our models. Let's look what would be prediction of our upper plate deformation above our models. And that is so. We can run our seismic model for 200,000 years. And what you see here is, this is velocity of let's say, relative velocity between this particular point and the rest of this boundary. And this is in millimeter per year. So basically, and each curve is different subduction zone with different geometry. And what you see that almost in all the cases, we have a very, very tiny deformation of the upper plate. And the reason is just very low friction, as simple as that. There is a very low mechanical coupling between the slab and the upper plate, and that's why deformation is low there. And only in the case when you have the maximum friction, which we suggest to be 0.05, you begin to have compressional deformation here, like in Central Andes, but also not so very large. And finally, we can test our models looking at predicted, just comparing predicted maximum magnitudes with observations. So here I put all earthquakes with magnitudes higher than 8.3. And you see some of them are indicated here. Let's focus on this Kamchatka one. This was degraded. So some people like Stein and Okal and several others, they suggested that actually it was not 9, but 8.8 or 8.9. So let's put it in recent position, this Kamchatka earthquake. And now we can compare our prediction. What is our prediction for the maximum magnitude? So for each subduction zone, we can put our range of predicted maximum magnitudes for a range of friction coefficients. And this is how it looks like. So this is our minimum friction coefficient, and this is our maximum friction coefficient. And you see that we fit very, very nicely, let's say, envelope of all this earthquakes. So it looks like that all this indicated here in earthquakes, they came very close to the maximum, so their theoretical maximum. But for instance, Sumatra 2004 was at least 3 times smaller than it could be. So hopefully it will not happen. So actually, because it's a very low angle, and so it didn't reach its maximum value. Now we can just look on what actually Raff and Kanamori wanted to look at. So this is mean shear stress multiplied by width of rupture zone here. And this is maximum magnitude suggested by our model. So actually, you see all the points for different geometries here. Actually, here is West Pacific. Here is East Pacific. So there is some, let's say, shadow of correlation here, but it is very weak. Correlation is very weak. The most important is, of course, the geometry of zone, and of course, subduction velocity doesn't play a role. So that's why Raff and Kanamori is not working. And now we are coming to conclusions. So long-term static effective friction is very low in subduction zones. Maximum magnitudes of the earthquakes are exclusively controlled by the factors that increase rupture width and rupture length, of course, because we assume that rupture length is scaled with rupture width. And the factors are lateral coherency of subduction channels, indicated by many other people, which is probably enhanced by the thick sediments. And actually, the low slabs dipping angle is the most important factor, and all these effects, so effects of the mechanical coupling and subduction rate are just a minor effect. And low friction and subduction in subduction channel results in neutral or compressive deformation in the overlying plate, and if it has a low angle of subduction. And all these modeling results fit quite well to observation. Thank you.